Hello everyone. Now, let me briefly introduce our work, titled ShowFace, Coordinated Face Inpainting with Memory-Disentangled Refinement Networks. Since the corrupted regions traverse multiple semantic parts, the face inpainting generally requires consistency within each semantic and coordination between different semantic parts. When the missing regions are large or the face contents are complex, face inpainting is challenging. This is the outline. It consists of 4 main chapters: Introduction, Related Work, Method and Conclusions. Now, let's start the first chapter. Face inpainting is an ill-posed problem, which aims to restore the corrupted regions with coordinated contents as long as they appear plausible. Recently, face inpainting has shown great potential in real-world applications such as interactive face editing and occluded face recognition. The next chapter is to introduce some related work. The first work is PD-GON. They propose spatially probabilistic diversity normalization inside the modulation to model the probability of generating a pixel conditioned on the context information. Spatially probabilistic diversity normalization dynamically balances the realism and diversity inside the whole region, making the generated content more diverse towards the whole center and resemble neighboring image content more towards the whole boundary. Meanwhile, they propose a perceptual diversity loss to further empower PD-GON for diverse content generation. The second work is TMAD. They propose a inpainting framework where texture generation is guided by a texture memory of patch samples extracted from unmasked regions. In addition, they introduce a patch distribution loss to encourage high-quality patch synthesis. However, the previous methods have some problems. They all ignore the content consistency within the semantics and the coordination between the corrupted regions and the non-corrupted regions. Then let's go to next chapter to introduce our method. We propose the coarse-to-fine Memory-Disentangled Refinement Networks for coordinated face inpainting, in which 2 collaborative modules are integrated: Disentangled Memory Module and Mask Region Enhanced Module. Specifically, the Disentangled Memory Module establishes a group of disentangled memory blocks to store the semantic-decoupled face representations, which could provide the most relevant information to refine the semantic-level coordination. The Mask Region Enhanced Module involves a masked correlation mining mechanism to enhance the feature relationships into the corrupted regions. Furthermore, to better improve the intercoordination between the corrupted and non-corrupted regions and enhance the intra-coordination in corrupted regions, we design InCo2 Loss, a pair of similarity-based losses to constrain the feature consistency. We first employ the coarse network to generate the coarse face. Then, the Disentangled Memory Module stores the semantic-level latent vectors from non-corrupted regions, pink line in Disentangled Memory Module, and provides the most relevant features according to the semantic-aware queries from the coarse face, green line in Disentangled Memory Module. Next, the Mask Region Enhanced Module fuses the features from the Disentangled Memory Module and constructs a correlation map to enhance the correlations into the corrupted regions. Finally, The fused features after mask region enhanced module are injected into the guided refinement network to get the final result. Let me briefly introduce how to update memory. To begin with, we compute the cosine similarity between the latent vectors of the coarse face and the corresponding memory slots. Then, we retrieve the memory slot which is most relevant with the latent vectors of the coarse face in each training batch. To ensure the authenticity of the memory, we use the non-corrupted latent vector from the non-corrupted regions in each training batch to update the most relevant memory slot. After updating the memory, we reconstruct memory-based latent vectors. To begin with, the cosine similarity matrix is computed by the first formula. Then, the soft scores A are formulated by a softmax operation. Finally, the memory-based latent vectors is constructed by aggregating memory slots with the soft scores. To enhance the feature representation of the corrupted regions, we propose Mask Region Enhanced Module, which consists of feature fusion and masked correlation mining. Since not every pixel in the inpainting task is valuable, we designed a patch-based correlation calculation, which is different from the self-attention based on pixel that is susceptible to interference. Finally, in face inpainting, it is unreasonable to only focus on corrupted region reconstruction. Meanwhile, coordinated face inpainting between the completed and the non-corrupted areas is also a key point. So we propose InCo2 Loss to further constrain the feature consistency for face inpainting. There are two steps to establish the InCo2 Loss, as shown in figure. In the pre-train phase, we employ an encoder-decoder-based reconstruction network to obtain the implicit representations of face from the middle layer. Then we employ the pre-trained encoder and the mask to obtain two representations of the mask and non-mask regions. Finally, we can compute the InCo2 loss by employ the representations previous. Then let's go to our experiments. This is the result of qualitative analysis and quantitative analysis. We conduct extensive experiments on CelebA-HQ and FFHQ datasets, which demonstrate the superiority of our method compared with previous state-of-the-art methods. Finally, the last chapter about conclusions. Our work is summarized as the following 3 points. Firstly, we propose the Memory-Disentangled Refinement Networks for coordinated face inpainting. Secondly, we propose 2 collaborative modules, the Disentangled Memory Module to establish a group of disentangled memory and the Mask Region Enhanced Module to enhance feature correlation. Thirdly, we design InCo2 Loss, a pair of similarity-based losses to better improve the intercoordination between the corrupted and non-corrupted regions and enhance the intra-coordination in corrupted regions. That is all. Thank you.